Hello Math 1093, this is Dr. P with one arcsine, many angles. So the idea of this video is I'm going to talk about some strategies for solving basic trigonometric equations like these. And when I say solve, I mean find all real solutions theta. Okay, in some of the My Math Lab for section 3.3, you're going to be asked, for example, to find all real solutions in the interval 0 to 2 pi. I'm going to talk about how to do that a little bit, but mostly I'm going to focus on how to find all of the real solutions, because if you can do that, then you can find all of the real solutions in a certain interval, like 0 to 2 pi. So we're going to start with this example here. We're going to solve the equation sine of theta equals -1/2. All right, so first of all, one common way that students think about this question, and it's not a bad way to start things, it's just not the complete solution. So number one way to start is to say, okay, what is the inverse sine of -1/2? Because that would be an answer to this question here. If I want to know an angle theta such that sine of theta is 1/2, that is exactly what this would be. Inverse sine of -1/2 would be an angle in the interval from -pi/2 to pi/2 that solves the equation sine of theta equals -1/2. So in other words, if I could solve this problem, I'd be on the right track. Now we might think, okay, what would be that angle? What would be the angle in -pi/2 to pi/2 that solves that equation? And I might address that question by sketching a unit circle and trying to find that magic angle between here and here, between -pi/2 and pi/2, that makes that true, that gives us a sine of -1/2. So that's going to be this angle here. It should be at y equals -1/2 there. So this angle would be -pi/6. So that would be one possible solution to this equation. So one possible solution to sine of theta equals -1/2 would be theta equals -pi/6. Okay, and that's actually exactly what the inverse sine of -1/2 is. But while this expression here, this inverse sine or arcsine, has exactly one value, this equation here has many possible solutions, and this is just one of them. So let's think about other ways that the sine of an angle could equal -1/2. This is one of them in this picture, but another one would be to have an angle which is over here, that points to the point that is the reflection of this point across the vertical axis. Take this and move it over here. All right, what angle would that be? That would be an angle of, depending on where you start and how you count towards it, this would be an angle of, I think, 7 pi over 6, because I'm taking pi, which is half of a rotation, and then adding 1/6 of pi more than that. So 7 pi over 6 would be another possible angle. So let's see if we can just think of any other angles. Okay, so we got -pi/6 and then 7 pi over 6. What other angles would give me a sine of -1/2? Well, I could do this one from here out to here, and it might seem like that's exactly the same thing as what I did the first time. But if I start at the horizontal axis and then go counterclockwise to this radius here, that's actually an angle measure of 11 pi over 6. And what if I were to start here at the horizontal axis and go around and keep going around until I come back to this radius? So that's 2 pi plus another 7 pi over 6. So that would be, let's just work that out, 2 pi plus 7 pi over 6, that's equal to 12 pi over 6, plus 7 pi over 6, that's equal to 19 pi over 6. So that would be another angle. And I could keep going. I could create as many of these as I wanted to. So how do I state in general what a solution to this equation should look like? So the general solution to this equation, one approach for writing this down is to focus what we're doing on a couple of specific angles. I'm going to pick these two because these are both in the interval from 0 to 2 pi. So those are the angles that take me here and here. Those are 7 pi over 6 and 11 pi over 6. All right, so now suppose I want to describe all of the angles that make this equation true, that make the equation sine of theta equals -1/2 true. All right, well, one way I can make that equation true is to take the angle 7 pi over 6, and then I can add any multiple of 2 pi to that I want. So k is an integer. Okay, let's talk about why that would work. All right, first of all, we know that 7 pi over 6 is going to take me to this radius where the sine is equal to -1/2. That part we know because we've worked on special angles for a while. But if I take that angle and I add 2 pi or some multiple of 2 pi to that, I'm just adding some number of complete revolutions around the circle, and I'm going to wind up in exactly the same spot. I could also take 7 pi over 6 and subtract 2 pi from it. That would take me back clockwise to this radius. So when I say 7 pi over 6 plus 2 pi k, I'm saying take that angle 7 pi over 6 and add any number of full rotations to it, any multiple of 2 pi. Okay, so that's one possibility. The other possibility is I can take this other angle, 11 pi over 6, and I could add any number of full rotations to it. That would also be a set of possible solutions. So now if I ask you, okay, look at this equation, sine of theta equals -1/2, how many solutions does it have? The answer is actually infinitely many, because I have these two solutions, 7 pi over 6 and 11 pi over 6, but each of those creates infinitely many solutions by adding any number of full rotations that I want. That's where those 2 pi k's come in. All right, let's talk about example 2, tangent of theta equals 2/5. You'll notice this time I organized the problem so that it would be a little bit harder for us to use special angles to solve the problem. All right, so number 2, tangent of theta equals 2/5. Let's first draw a picture that might sort of suggest to us where we might find solutions to this, but we're going to use a calculator to help ourselves out here. All right, so draw a circle. This is kind of a pathetic circle. Okay, and it's close enough anyway. All right, how would I draw a picture of an angle whose tangent is 2/5? Well, I could think, well, the tangent of an angle can be thought of as a y-coordinate over an x-coordinate, so I could let y equal 2 and x equal 5, figure out what the radius is later. So if I want y equals 2 and x equals 5, I'm probably going to be somewhere around here. There we go. So I'm going to have some angle theta that takes me to the point 5, 2. And just for reference's sake, I don't know if I'm going to need this information, but the radius of that circle is going to be square root of 29, the square root of 5 squared plus 2 squared. All right, so that's one way of getting an angle whose tangent is 2/5. And to find out an approximate measure for that angle, what I'm going to do is I'm going to say theta is equal to the inverse tangent of 2/5. This works because my angle's in the first quadrant, which is part of the range for the inverse tangent function. So I'm going to input into my calculator arctangent of 2/5, and it's going to give me 0.38 radians. So I'm going to write that down. So this is 0.38 radians. And in the picture that kind of makes sense. This arc length here is about 0.38, or about, yeah, it's about 38% of a radius length here. Okay, so that's this angle measure here, is 0.38 radians. But again, there are a number of possible angles that would give me a tangent of 2/5, and the one you see in this picture is just one of them. Okay, so just thinking in terms of quadrants, no angle in this quadrant is going to work, because in this quadrant, y is greater than 0, but x is less than 0. So that means that the tangent is going to be a negative number, less than 0. In this quadrant, y is less than 0, and also x is less than 0. So the tangent is a negative divided by a negative. That's a positive. So I actually have some hope that in this quadrant I'm going to find a solution. Over in the fourth quadrant, I have y less than 0, but x greater than 0. So the tangent is negative. I'm never going to find a tangent of 2/5 down there. But I think I will find one in the third quadrant. And one way that I can do it is I can create another radius that starts here and goes out to the point -5, -2. That would work because the tangent of this angle from the right-hand axis down here, the tangent of that angle would be, what would that be? It would be -2 over negative fifth, which is the same as 2/5. So that has the correct tangent as well. Now, what relationship does that angle have with the one I drew for the first time, which is that theta there? You'll notice that this angle, I'm going to draw this in a different color now. This angle is theta, okay, that's theta, plus a half of a rotation. So that angle there is actually going to be this theta, which I'll just call theta 1 for right now. So another possibility is going to be that theta 1, so theta is equal to this theta 1 here, which was 0.38 radians, plus pi, which is half a rotation. And if I take that angle and add another pi to it, so start here and add another half a rotation, I get back to this one, which is another angle measure where my tangent is 2/5. So I could actually take this theta 1, this 0.38 radians, and I could add any multiple of pi that I want, as long as k is an integer. Okay, so the general solution to this equation, the general solution is going to be theta equals 0.38 plus k pi radians, where k is an integer. All right, one way of interpreting this solution, or one way of making it make a little more sense, is to realize that the tangent function, unlike the sine and cosine functions, the tangent function actually has a period of exactly pi. So if I have some value that gives me a tangent of, let's say, 2/5, if I add pi to that, or any multiple of pi, any integer multiple of pi, I'm still going to have a tangent of 2/5 because I'm just adding some multiple of the period. So that's another way of thinking about that problem. Okay, so the major moral of this video is if I want to solve equations like these two, like the two presented here, I can use inverse trig functions on my calculator or use my knowledge of inverse trig functions, like I did on that first example, to find a single value. But in order to find other values, I need to think carefully about all 4 possible quadrants of the unit circle, or whatever circle I'm working with, and then also think about adding full rotations or half rotations as appropriate. In this case, I added full rotations and got other viable solutions. In this case, I added half rotations and got other viable solutions. And that's going to be a theme throughout this section.